हेलो।
हाँ हेलो अडेपू। हाँ आवाज़ आ रही है पर थोड़ी कम आ रही है आवाज़।
हाँ सौरभ, अभी आ रहा है? सही आ रहा है?
हाँ हाँ ठीक है, थोड़ा वॉल्यूम बढ़ा सकते हैं क्या?
हेलो। हाँ सौरभ, अभी
हाँ अभी बेटर
मतलब
बेटर है।
वॉइस क्लियर आ रहा है?
हाँ बेटर है बेटर है। क्लियर क्लियर।
इधर म्यूट।
अरे नहीं, म्यूट नहीं हूँ। आपको आवाज़ आ रही है मेरी? अडेपू आवाज़ आ रही है?
हाँ अभी आ रहा है, अभी
हाँ
आ रहा है।
हाँ हाँ हाँ।
क्लियर है, अब सही जा रहा
एक
है।
बार पीपीटी शेयर कर लो।
अगर पूछ लीजिए, क्लियर है, अब सही जा रहा है, पहले कम आ रहा है।
पूछ लो।
सर आवाज सही आ रहा है अभी?
हाँ हाँ ठीक है, आवाज़ ओके।
ठीक।
एक बार स्क्रीन शेयर कर लेते हैं, एक बार
हाँ
पीपीटी भी।
स्क्रीन शेयर चेक कर लो।
हाँ ये पीपीटी है।
हाँ।
अच्छा।
पीपीटी मोड में डालो।
हाँ ओके,
ओके
विजिबल है।
विजिबल है।
एक सेकंड, एक सेकंड। हाँ, ये स्लाइड्स मूव हो रहा है।
हाँ मूव हो रहा है, ओके।
ठीक ठीक ठीक।
हाँ हाँ।
चेक कर लेते हैं।
तो तो सौरभ, मतलब इफ एवरीबॉडी इज देयर वी कैन स्टार्ट। हाँ
अडेपू बस 2 मिनट और दो।
हाँ,
कुछ
ठीक है ठीक।
पार्टिसिपेंट्स अभी भी ज्वाइन कर
हाँ
रहे हैं।
ठीक 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 है ठीक। म्यूट म्यूट कहाँ आ गया? म्यूट ऑप्शन कहाँ आ गया?
क्या करना है?
म्यूट म्यूट।
यहाँ से कर सकते हैं। ये म्यूट म्यूट।
ठीक है शुरू करते हैं फिर अडेपू, है ना? अभी तो I think it's getting late. So, good morning, everyone, and welcome to the day 8 of our training program. And we will be starting today with the two sessions related to the design of water resources projects. And for delivering these two sessions, we have with us Shri Adepu Raghavendra ji, who is Deputy Director in Embankment East and Northeast Directorate of CWC Headquarters, posted at New Delhi. Shri Adepu ji is a Central Water Engineering Service Officer of 2013 batch, also my batchmate, and he joined CWC in the year 2015 and was posted initially as Assistant Director in the Concrete Machinery Dam Design North and West Directorate of CWC. Before joining CWC, Shri Adepu has also served for about 4 years in Webcos Limited, where he was associated with the preparation of feasibility reports and tender documents for hydroelectric projects. Upon joining CWC, initially posted in D&R wing. Thereafter, he also served as assistant director in the monitoring and appraisal directorate of KGBO in Hyderabad. And currently, Shri Adepu is serving as deputy director in Embankment E&NE directorate. So, with this brief introduction of Shri Adepu Raghavendra ji, I welcome him to this training program, and I request that Adepu, you may please start the session.
Yeah, thank you, Saurabh, for introduction. So good morning to all. So hope everyone is able to see the screen. If anybody is having problems, please kindly let us know. So, today my topic will be overview of design of water resources. So you all know that in CWC we have 3 wings. So by now you might have known all these things about these 3 wings, and mostly you are working in RM wing. So we have 2 other wings. One is WPNP and design wings. So in design wings we do design for all the water resources projects, components, everything. So we will see in, every aspects in detail here. So if anybody is having any doubt, try to keep or post your comment or observations or questions in chat box, and we will take up all the questions at the end of this session. And in the meantime, also, if you have any doubts, kindly note it down and take my number from Saurabh, and we can also be in contact even after the lectures also. So because right now, as a JE, you will be posted in the field offices mostly, where you will be collecting the data, site observations. So you might not be knowing why design is required. So at the end of the session, I think you will be able to appreciate how whatever you are doing at the sites, at the river sites or the remote areas. So how that will be useful for the design of all these water resources projects. So we will see all those aspects. So that's how you should know at least what we will do in the design wing of this CWC, so that when you become AD or even DD, so at least we expect at least you people should come into D&R wing and serve this D&R wing, because many of the people think that designs are very complicated and it's very difficult to do, and most of the people will prefer WPNP or RM wing only. So but I request, please try to take one topic from today's lecture. Like, there are so many aspects, I will try to explain you. Try to what you call take one topic of your choice and try to learn something from whatever topic of your choice. So let's go ahead with the presentation. So today, if you see on the screen, this is I think most of the people know this is a Hirakud Dam. So in the Hirakud Dam, if you see, there are many components. The first component, if you see that the grass portion on the downstream, you can see that is the embankment dam. Then we go ahead, see, these are the gates. Like, you can see this big structure that we call it as a gantry crane. So that portion and the spillway portion, we will be having gates. So the other portion is concrete and masonry. The next portion is powerhouse. The next portion is canal and channel. So these are the major 5 directorates in design and design unit. In designs, there are total 5 units. One is hydrological unit, one is a dam safety unit, and other 3 are completely design wings. So these 3 are divided into as per the regions of the country, like northwest, south, and east and northeast. So I am currently working in east and northeast wing of these designs. So all these 3 units will be having all these 5 directorates. So one directorate will be embankment directorate, one directorate will be concrete and masonry directorate, and one directorate will be gates. One directorate will be dealing with the powerhouse components, so that we will call it as hydel civil design directorate, and one directorate will be dealing with the canals and barrages. So hope everybody is clear about this design unit, because we will be having all these 5 directorates, and each directorate will be doing the specialized. So I am right now I am in embankment directorate. So I'll be dealing all the aspects related to embankment. So embankment designs, embankment safety. Whenever there are any failures or any specific problems by state governments, so we will be dealing only with the embankment aspects. So I'm also having additional charge of concrete directorate also. So wherever this concrete dam issues will come, I will also be doing this concrete uh, aspects. So there will be so many JEs in your team will be from mechanical background also. So mechanical, I suggest people to just take up these gates because in CWC it's a general practice that mechanical background people will be posted in gates directorate. Uh, but some civil engineering candidates also are working in gates directorate, but mostly preferable for mechanical. So when you are thinking that mechanical, why I am here measuring the river discharge at the site, just it's just a passing your JE time and AD2 time. Once you come to the headquarters, try to prepare this posting in gates directorate so that you can apply your all your whatever mechanical background engineering knowledge to the gates directorate. So this is the background of our design unit, and these are the different components how we separate into our design different directorates. So if we see further, so because all the water resource projects will start from the dams. So there are different types of dams. So I think by now you might be identifying these different dams. So let's go ahead with one each one. So the first one you can see on the screen, it's a concrete dam. The other one is earthfill dam. So you can see it is a failed section. Like this is the dam in Rajasthan, Garada Dam. So this was failed in the first filling itself. So that's the section we are seeing here in the earthfill dam. You can see here it's a complete same color material, right? So that this dam we will call it as homogeneous earthen dam. So other dam is rockfill dam. So it's nothing but that just updation of this earthfill dam, because as the height of this dam increases, we will we will be having some clay core in the central portion, and also we'll be having some coarser materials. And these fine materials it will be what you call sustained for the only some heights only. So this rockfill dam you are seeing, it is the Tehri dam. Tehri dam we all know it is two fill dams. So the other type of dam is masonry dam. So masonry, it's a old concept. Nowadays we are either going for the concrete dams or earthen dams or rockfill dams. But masonry is old dams, but still there are so many dams built in India from long time. So there will be so many issues. So we should know the uh, types of masonry dams, what are the problems, what are the designs, and etc. So design wise, everything concrete and masonry will be mostly similar, but the problems will be different because here we will use mortar and the joints. You can see in the image also there is some seepage to the dam body. So these are the different challenges. So next is CFRD. CFRD full form is concrete face rockfill dam. So if you see one image just here, it is completely homogeneous dam, right? So what is the purpose of any dam? The purpose of any dam is to store the water and also to arrest the seepage either through the dam body or through the foundation. So if the soil is completely able to stop the seepage, we can go for the homogeneous. But it's very difficult to get clay material or particular that kind of material, right? So that's why we are going for the clay core material in the central. In the outside, we will going with the rockfill dam. That's why this rockfill dam is coming. So even in some places, if you don't get clay, so what is the option? How do you store that? How do you stop the seepage? So we will be having this in the upstream. We will be having concrete facing. So the remaining material will be rock fill, but in the upstream we will be stopping the seepage using the concrete. So that is why it is concrete phase. So in the upstream phase, it is having concrete phase. So that is why concrete phase rock fill dam. So the other kind of dams, arch dams. So in India, we have very few arch dams because the design is very complicated, and also to have the arch dams, we should be having this strong You can see in the in the picture. So these both apartments.
सर हेलो
Yes, yes, yes.
सर आवाज आपकी बीच बीच में कट जा रही है बहुत देर तक
Okay. अभी आ रहे हैं?
हाँ डेपू,
अभी
अभी अभी तो
कंफ्यूज
ठीक है। पर अभी जैसे थोड़ी देर पहले के लिए 10 सेकंड के लिए वो डिस्कनेक्ट हो गया था, ऐसा लगा।
अच्छा, मे बी मतलब वही ना, अभी इंटरनेट
हाँ हाँ हाँ।
हो
ठीक है।
चुका है सर बीच में
अभी
बहुत
अभी
देर
अभी ठीक है, तो प्लीज कंटिन्यू। पर
हाँ
बीच
हाँ
बीच
हाँ
में कहीं कहीं पर, सो आई रिक्वेस्ट द पार्टिसिपेंट्स कि आप लोग प्लीज थोड़ा पॉइंट आउट कर दीजिएगा जहाँ पे भी सिमिलर इशू आता है आगे।
या that's why I'm going मतलब I'm going on repetition mode. In each slide I'm just explaining 2 times. So because because this slide you can see we are having all these different types of dams. There are many other dams also, like you can go.
फिर नहीं आ रही है सर आवाज
Again, same problem, sir. About this not coming.
Hello.
Sir,
भी आई है जस्ट फिर नहीं आ रही है सर
Just अभी आ रहा है क्या?
अभी आ
yes,
रहा
sir.
है
अभी
सर
तो आ रही sir.
Yeah, I will just go very slowly. But meantime, whenever there is any disturbance, just try to see on the slides, because see, uh, this is only regarding the design overview, right? But at least you should able to know the difference between these dams. So everybody is clear about this difference between these dams: concrete, earth filled, rock filled, masonry, CFRD, and arch dams. Hello. So shall we go ahead with the others? Next slide.
Yes, sir.
Yes, sir.
So like I have already explained, this is concrete phase rock fill dam. So in the upstream phase, we will be having this concrete phase. So you can see here. So first we will complete the embankment dam portion, and in the upstream phase, we'll just have these concrete panels. You can see on this screen. So we'll be having these concrete panels constructed in a panel wise. So other important dam is roller compacted concrete dams. So can anybody tell any dam existing in India, this roller compacted dam? Anybody? Yeah, in Maharashtra we have this Gadgar dam. So Gadgar dam is completely RCC dam. RCC means roller compacted concrete dam. So in roller compacted concrete dam is just like a concrete dam, but you can see the steps here. So why these steps are here? There are so many steps, right, on the screen. So it's just like a earthen dam type construction. We will be placing concrete in layers. Each layer we will place concrete, then we will be rolling it, just like in any earthwork. In all earthwork, what we do, we just place some earth in different thickness layers, and we will roll it for some 2 to 10 passes with using heavy rolling machines. So it's the same concept. Concrete also we will place concrete in layers, and we will roll. So that's how you can see different steps here. And even you can see the water also. Each step while it passes, the energy gets dissipated. So you can see in the bottom image, you can see the spillway. So there is no need of providing any spillway here. And like I already explained in the beginning, we have 5 units, right, in design wing. So one exactly deals totally deals with the hydrological aspects. So you can see here spillway. So this water, what will be the design flood? Everything will be dealt by hydrology unit of this design wing. So in design total we have 5 major units. 3 will be completely dealing with the designs, One will be dealing with this design flood aspects and how much whatever you are measuring the data at the site, that those will be compiled at some level. Then we will use those data, that data to identify or estimate this design flood. So that design flood we will be using for these dam designs. I think now you are understanding your value, whatever you are doing at the site. So that is very crucial for all this planning of these projects. So this design flood and all the hydrological issues will be separately dealt by one unit of these designs, that is HSO unit, and the other unit is dam safety unit, DSO, dam safety organization. So any dam issues, dam safety issues, because in India we are having one project, dam rehabilitation and improvement project. So dam rehabilitation improvement project in India, we all know there are totally 6,000 dams. In 6,000 dams, there are 700 dams which are very old and which require some repairs. So for each dam repair requires so much of money. So that money amounting to more than 10,000 crores, even 20,000 crores. So that money is being funded by World Bank, and some money is funded by central government of India, and some money is being borne by state governments. So that dam rehabilitation and improvement project DRIP. So that those things, everything will be dealt in dam safety organization. So total five. One is hydrological HSO, DSO, and three design wings. So whatever you are doing at the site, that data will be useful for the HSO to estimate these design floods and water availability, everything. So there are other some small dams, rubber dams, because you can see the height also in the pictures. Is just to, you can see in the bottom image, whenever there is you want to increase the storage, or if you want to store the water, just inflate this rubber tube, so that rubber tube will expand. So the 2 to 3 meters of water you can store behind this rubber dam. So whenever we don't require, then just deflate it, and again it will come back to its original position. So whenever it's useful for very small purposes, like in check dams or in small nalas, where you want to have this 2 meter or 3 meters diversion. For that purpose, we will use rubber dams. So hope everybody is clear till now. Hello? Can anybody?
Yes, sir.
Yeah. So we will go into some more in what you call detail. So how to fix this dam axis. So I think many some of the JEs are working in investigation divisions also among you. So they will be doing all they are involved in this investigation of these projects. So the first investigation in any project will be compiling of this topographical data. So whatever you are seeing in these yellow colors, it's all contours. So I think everybody knows what is contour, everything. So when we get this topographical data, we have to see different axes. Like you can see that I have marked here EE, DD, like all these things, right? These are different dam axes, because we don't know, right, where exactly we can plan a dam. So first we have to study different dam axes, and we have to evaluate each dam axis whether it is best possible dam axis or not, because you can see some dam axis, it will be very lengthy. Some dam axis will be having very small, shortest portion of the dam, and some you can see as we go downstream, we can have more water can be stored, right? So there are different aspects. We have to see the geology. Geology means what is the rock available, what is the soil strength available, uh, what are whether we can keep that foundation on that particular geology or not. So we have to see the geology, we have to see the water availability, whatever you are doing, whatever you are collecting, that is water availability. And we have to see the narrow portion. Wherever possible, we have to use the narrow portion to select the dam axis. So to do the dam selection, site selection, first we have to do some, we have to study these 3 or 4 different axes. Then out of these 3 4 axes, we have to see the best alternative based on the geology, based on the water availability, based on the our planning of the components. That I will explain in the coming slides. So like this is one more dam axis, one more project. You can see here here also we have studied 5 different axes, 1, 2, 3, 4, and 5. So like this 5 different axes we have to study, and among these 5 different axes we have to narrow it down to 1 or 2, and in 1 or 2 whatever matlab most feasible. So we have to do some more investigations to decide between these 2 axes. So like this we have to finalize the dam axis. Once we finalize the dam axis, remaining components like I told, we at the dam axis we can estimate the dam design flood, uh, then we can design the length of the dam, everything that I will cover in the coming slides. So this I have already explained. So if you can see here different dam lengths. So obviously we'll prefer this shortest one. This CC, like section CC is the most suitable location for the dam. If there is only length is the criteria. If there is because why this length is the criteria, because if you increase the length, obviously cost will increase. So projects will not be become viable. So most of these projects like whatever irrigation project, hydroelectric project, drinking project, we all do some cost analysis, benefit cost ratio. So benefit cost ratio means whatever the cost you are incurring on this project and what are the benefits you are getting from the projects. Just we'll do analysis, what are the benefits and what are the costs, just having this ratio, benefit cost ratio. So it's always better to have benefit cost ratio more than one, because it's a general practice, right? Whatever cost you are putting on the project, at least you should get profit more than the cost of the project. So that's how you do the benefit cost ratio. So based on the benefit cost ratio, you will also able to select the projects which will be taken on the priority. So all this whatever you are doing, even whatever DPR, the major basic purpose of this DPR is to evaluate the technical feasibility and also financial feasibility. So the technical feasibility, what I am saying is, we have to see all this hydrology, geology, and dam designs, and financial feasibility in terms of benefit cost ratio. What are the benefits we are getting and what is the cost associated? So to minimize the cost, like this, we can minimize based on this dam selection, because if the dam length is more, obviously the cost will be more. So benefit cost ratio will come less, obviously. So that's why we have to select the dam length in such a way that we can minimize the cost. If the other things are if the other things are same, like if you say if the geology is weak, we cannot do anything. If the hydrology, if the water availability are changing, then we cannot decide anything. But if the geology, water availability, all the aspects are same, then the dam length is the critical thing. If the dam length, because if you see in Hirakud dam, it is a 22 kilometers embankment dam. In nowadays many dams are also coming, they are coming 4 kilometers. So in the 4-kilometer dam you cannot have concrete, right? 4-kilometer dam placing concrete, it will
Your voice is not audible.
आवाज नहीं आ रही है।
सर वॉइस नहीं आ रही है।
रहा है।
सर वॉइस नहीं आ रही है।
अभी आ रहा है क्या वॉइस?
सर
यस
अभी सर आया है।
यस सर।
हाँ, just I am coming again. You can able to see the screen?
Yes sir.
Okay. So whatever discussed till now, everybody is clear?
Sir, up to last slide it was clear.
No, sir, not this slide.
Yeah.
Last slide.
Yeah. Up to this slide, everybody is clear, right?
Yes, sir.
Yes sir.
Yeah. So like this, we have to finalize this what you call dam axis. That the dam length is the first important criteria. Other criteria also I will try to explain. Just from here we can see the layouts. Like we have completed this different types of dams. We have completed how to select this dam axis. Why this is very crucial at the first step. Then we will see different layouts, because you see all the water resources projects we will be designing for either for hydro project or for irrigation project or for drinking project, right? So each project will be having different layouts. So on the screen you are seeing is the hydro project. So this is a Ganol hydro project in Meghalaya. We have just completed 1 year back, but all the hydro projects mostly of this layout only. So the first will be dam. Then from the dam, the water will be going through the HRT. HRT means headrest tunnel. Then from the headrest tunnel, the water goes to surge shaft. So surge shaft. Then from the surge shaft, using the penstocks, the water will go to the power house. At the power house, we'll be having these turbines where the power will be generated, and from the power will be transmitted using the transmission towers. Whatever transmission towers you will be seeing on the vertical in the general places, so that power will be supplying from these power houses. So the purpose of this HRT is to just to divert the water from the dam to surge shaft, and from surge shaft to power house by penstocks. Okay, so this surge shaft, the purpose of this surge shaft to, because this the length of this HRT, sometimes it will go up to 10 kilometers, sometimes it may be 1 kilometer. So depending on this length, sometimes if you suddenly close this power house, like you see, there are some grid failures. If anybody had heard about grid failures, because in India we have these power grids, right? So earlier we used to have 4 power grids: northern region, southern region, and eastern region, and western region type. So each grid, because there are so many power projects, we have thermal power projects, solar projects, hydro projects. So all will be supplying power. Whenever there is some disturbance or some disturbance in the frequency or other things, sometimes grid will fail. So that means there will be sudden closure of this power demand. So the power house will stop the turbines automatically. So when we stop automatically, there will be some sudden shock, right? Sudden shock in the water conductor system. We generally call it as a water conductor system. So in this penstock or in this headrest tunnel, if you suddenly close these gates at the power house, so there will be some water shocks, water waves. So to observe these water shocks, we call it as hammers, water hammers. We will generally be having surge shafts. So the basic purpose of the surge shaft is to observe the water hammer, water shocks. So this is the general layout of this hydro project. We will be having dam. We will be taking this water through headrest tunnels. Then we will be having surge shafts if it is required. if not required, if the length is very less, we can avoid the surge shafts. Then from surge shaft you take these penstocks, and we will generate this power at the powerhouse. So this is the layout of any hydro project. There are other different layouts also. I will explain in the coming slides. So this is a irrigation project. So generally we prepare irrigation command maps like this. This is one irrigation project in Adilabad district of Telangana. So the yellow color in shaded portion you see, that is a command area. So all these pink colors and red color line, this is the canal. You can see this. This is the dam. So this is the dam. From dam you can see this right side canal. It is going like this, and wherever this yellow portion is there, that is the command area. That is where we are supplying the water to have the irrigation. So if you see that same layout in GIS, because most of the people you will be doing using RGIS and other GIS platforms also. So in GIS, that image we try to provide here. So this is the dam, whatever we have created the storage. So from the dam you can see one canal is off taking like this, right? So obviously at the just near to the dam, there won't be much requirement of water, because water will be groundwater will be always high. Then as you go down, you can see the different branch canals. So each branch canal you can see in the what you call denominations, some 369 acres, 59, 195 acres, like that. So each branch canal is planned accordingly. So first we have to estimate the command wherever you require the command. First you estimate the demand of the water. Accordingly, you can design these branch canals. So this is the layout of irrigation project. So we have seen the layout of irrigation project. So irrigation project layout will be looks like this only. If this is the right side canal, you can also plan for the left side canal. And there are ridge canals. That's a separate detailed subject. But you should know what is the layout of this irrigation project, how this irrigation project layout looks like. So this is how we can plan irrigation project and its layout. So now we see in further detail of this hydro project. So like I told, first we will have this dam, concrete dam. So from the concrete dam you have to take the water to the powerhouse. So that's I've already explained. We will take the water through the headrest tunnels, right? So but before the headrest tunnels also, what happens? All the water, because these are all placed in the rivers. So in the rivers, in the flooding time, what happens? Because most of the people you will be understanding, right? Why you measure this sediment data? There are so many sites, right? GDSQ sites, right? So the GDSQ means sediment is you are measuring. The sediment is the data we are using in hydro projects. So at least now you are able to understand the importance of the sediment data measurement at the sites. So in the flood seasons, what happens? In the non-monsoon times, in the very lean seasons, you will be having clear water. But what about in the monsoon seasons? You will be having this sedimented waters. So, but if you allow this sedimented water to flow through the turbines or through these tunnels, it will erode the tunnels, and also it will damage the turbines. So it's generally not recommended to have this sedimented water. So to avoid the sedimented water, what we'll be doing is, so we all know this water will be diverting through these tunnels. So these are the desilting chambers. So you can see here, these are the desilting chambers. These desilting chambers, what they will do is, they will collect the sediment. So because you can see the dimensions also. I'm not talking technical, because first you should able to know this, at least at the end of this topic, if you know this terminology also, at least you can able to, even after 1 or 2 years, at least you know this terminology. That's more than enough for this lesson, for this session. So these desilting chambers, what they do is, whatever the sediment is coming through these tunnels, that will be trapped here. You can see the size also, size increase. Initially the tunnel size is very less. As it reaches to desilting chambers, the size is very big. Why it is big? Because as you increase the size, the velocity is reduced, by reduction in the velocity, the sediment will get deposited. Whatever the sediment deposited in this desilting chambers, that sediment we will again flush it through using silt flushing tunnels. And the clear water, whatever the clear water, because sediment will be deposited at the bottom, clear water will be at the top. So from the top, you will take this water again to the power hoses. That we will see here. So this is the complex layout. That's why I have explained with the preliminary layout. So if you see the complex layout, the HRT, head-rest tunnel, we have seen in the previous slide, up to the HRT, how the water goes, how the water travels. The water travels through the intakes, through this desilting chamber. Now we have removed the sediment. Now from the desilting chambers, we have connected that water to the head-rest tunnel. Then from the head-rest tunnel, the water goes to surge shaft. Then the surge shaft, it goes to the pressure shafts, pen shafts, to the power hose. So just you can try to read these words on the screen. We have machine hall. Machine hall means power hose hall, where we have these turbines. Like then we told I have told that after the power generation, we have to transfer that power, right, through the transmission this system. That's why we use these transformers. You can see the transformer halls. In some projects, what happens, there is a requirement of downstream surges, because in the downstream also we have to have this hammers, water hammers. So again, when you go into detail, you will understand this purpose of this downstream surge galleries, all those things. But the basic idea is you should have head-rest tunnel, you should have surge shaft, you should have pressure shaft. Then you should we will have the power generation in the power hose or machine hall. Whatever the power we have created, whatever the power generated, that will be transferred through transformers. Transformer, what is the purpose of transformer? Because in the power hose, we will be generating power hose at the 11 kV or 20 kV, very low voltage. But to supply to the long distance, suppose you see these hydro projects are located in very remote areas. Some projects are located in Arunachal Pradesh, some projects are located in extreme Himalayas, some projects are located in extreme far ends of the rivers. So from there, we are getting the power to the in Delhi, whatever, in Pune, in all the cities. How we are getting this power through the transmission lines. So this transformer does this stepping up. So the whatever the voltage we are generating in the power hose, we have to step up. From that step up, after the stepping up, it's very convenient to transfer the electricity to very long distance, even 1,000-kilometer distance also we can transfer. So that's the basic concept. Just I am explaining here for your knowledge. But generally, we don't deal all this electromechanical, this power components, power transfer. We don't deal in CWC. In CWC, what we deal is a dam. We all do the designs of this head-rest tunnel. We do the designs of the surge shaft. We do the designs of pressure shaft. We do the designs of power hose. Only power hose dimensioning only. We don't even design the turbines. Turbines and all these transformers will be dealt in either CEA, Central Electricity Authority, or it's a all the private companies, because there are many private developers are also there. They can also do these designs. So in any project, like if it is a irrigation project, if it is a hydro project, in CWC, along with CWC, we have to involve with other agencies. So generally, other agencies means like we are only involved in water sector, right? So, but there are so many other components or so many other agencies we require. Like I already explained, we need a requirement of geological data. So for the geological data, we involve with Geological Survey of India, GSI, and for any dam, like say if we are placing 100-meter dams, so we need to do concrete testing, we need to do material testing. So for the material testing, we need some other agencies help, right? So for that, we have this Central Soil Material Research Station, CSMRS. CSMRS is also under our ministry only, Ministry of Jal Shakti only. Under Ministry of Jal Shakti, we have CWPRS just next to the Pune, our NW Pune. CWPRS is there, CSMRS is there. So CWPRS generally does this, all the studies, water, like when the spillway, from the water flows through the spillway, how the water will flow, whether the water flow is as per our design or not. They do the model studies. CWPRS does the model studies. CSMRS, Central Soil Material Research Station, does the testing, material testing, and GSI, Geological Survey of India, will provide us the all these geological information data, and even if we require Survey of India, Survey of India also we can collect this topo maps, contour data, all those things. So while doing the designs of all these water resource projects, it's not we only individually we do all these project designs, everything, but we need the collaboration from all these agencies, even remote sensing also, NRSC, ISRO. We have to involve those organizations also, and if it is a hydroelectric project, we have to collaborate with Central Electricity Authority. So I will explain here. In field offices, we have monitoring and appraisal units, right? So monitoring and appraisal units, they will be appraising those projects of irrigation projects only up to certain certain irrigation command. Like we have in irrigation projects, major, medium, and minor. So minor and minor projects are even less command area projects only will be dealt in monitoring and appraisal directorates of field units. Wherever you are posted, you can find out. You can now appreciate their importance, monitoring and appraisal directorates. So they will be doing all this appraisal of these irrigation projects up to certain commands only. Like minor projects, like minor project means 2,000 hectares. So those projects only they will do the appraisal there. If major projects like more than 10,000 hectares, they will just forward it to CWC headquarters. So CWC headquarters do all these appraisals. So that is for irrigation. So if it is hydro project, CWC is not having the mandate of appraisal of these hydro projects. Appraisal of these hydro projects lies with the CEA, Central Electricity Authority. So Central Electricity Authority, while appraising this hydroelectric project DPRs, they will forward the DPR to CWC, because all the civil components, dam, headrest tunnel, surge shaft, power hose, all these components we will be examining. So that's how the appraisal process. That's how we are involved in irrigation and also hydro projects appraisal. So hope everybody is clear now about your monitoring and appraisal directorate and how you collect whatever data you are collecting, how useful for the design of all these water resources projects. Even the sediment data is very, very useful, because most of the dams gets filled up with the sedimented. Like if you see the Salal Dam in Jammu Kashmir, it is completely filled up with sediment. So the basic purpose of our dam construction is now getting lost, right, because of the sedimentation. So that's how whatever you are observing the data at the site, that is useful for all our design purposes. So moving ahead, so these are the different layouts of the hydro project. So you can see the hydro project layout here. The dam is here. You can see so many lines, right? So on the both abutments, like both sides, you can see this white color is a river. So river left side, we have some tunnels. In the right side also we have some tunnels. So this is a very complex layout. If you see further simple layout, you can see here the same layout. The first image, we can easily optimize into the second layout. So that's how we will examine generally layouts. So we generally avoid the complex layouts. So complex layout means you can see all these are the tunnels. Whatever you see in the first image on the both sides, all these small dots, these are all tunnels. Whereas in the second image you can see all the tunnels are placed on the one side. So that's how when we do the appraisal in our design units, we also check for this different dam axis locations and also different dam layouts, project layouts. You can see this project layout very complicated, right? Whereas in the second image, you can see it's a very simple layout. All the tunnels are located at the one place. So why? Because geology is very complicated. So that's why I have told in the beginning itself, because you are at the very starting of your career. I think you should start some topic of your choice. You can take geology, even hydrology, dam designs, or even irrigation, canal designs, or even remote sensing. So that's so, because geology, like I told, is very complicated, because in the one bank, in one side of the river, you will be having different geology. in another side of the river, you will be having completely different geology. That's how we should avoid on the both sides tunnels. If the geology is good, then it's okay. But nowadays, what happens in Arunachal Pradesh or in other northeast states, we are planning very high dams, more than 100 meters, 200-meter dams. So in the 100-meter, 200-meter dams, the geology plays the important role. And also in Himalayas, excavations, in every tunnel's excavation, there will be some problems will come. So to avoid those excavation construction problems, our layout, our project should be very simple type. So that's how we have prepared the second image. So this is for the Upper Siang. So Upper Siang project, earlier they have proposed this with the first photo, whatever shown here in the top photo. So now we have changed it to, almost we are changing it to the second image. So that's how we are optimizing the layout and optimizing the project based on our construction experience and also geological and all other aspects. So again, same other layout, because sometimes it is not feasible, because you can see dam, we have dam, and just downstream of the dam we have this power hose. One side we have to take this headrest tunnels, like I already explained in the previous slides. Water will be diverted using tunnels only, headrest tunnels. But when you do the construction of this dam, this area should be water dry, right? Because all these dams, in all these three images, you can see there are some small copper dams. So we call this as a copper dams. Copper dams purpose is to give this entire stretch of this dam area a dry area, because in the flowing water, the construction of dam, any activity is not possible. So to start the construction of any dam, we will be having that water free area so that the water will be diverted using before this copper dams only. So you can see here this is also copper dam. So the left side, the tunnels are used for the diversion of this waters during the construction time. So this entire time, this entire area will be dry, and we will construct the dam using this tunnel. The water will be diverted through this here. So once the dam is completed, we will remove these copper dams, and we'll store the water in the dams, and we'll divert the water through the headrest tunnels, and we'll take the water to the power houses, and we'll generate the electricity. So now we'll see the different issues. General, what will be the issues will be coming in different components. So this is the dam. So in the dam, we will see. Obviously, I already explained till now the foundation issues, because as the dam height increases, everything is stress, right? If you have a very small dam, very small stresses will come, small load will come. If the dam height is more load will come. So we have to see your foundation, whether the existing rock or the available foundation can able to take the load or not. And shears, this is a new term. Just I will explain brief, because you see, wherever you have this foundation, because it's all formation, it's a formation of this earth, right? Formation of earth and rocks. So it's completely either igneous, sedimentary, or metamorphic, right? So while forming these igneous rocks, sedimentary rocks, and metamorphic rocks, in between these rocks, there will be some weak layers. Like suppose in some areas you will be finding granite, some areas you will be finding sandstone, some areas you will be finding limestones. But it's not continuous. If you excavate 100 meters also, it's not sure that you will find completely 100 meters same rock. There will be so much variation in the rock as you go. Suppose past 10 meters you will get good rock, then next 1 or 2 meters you may get weak rock also. Those weak rocks we will generally call it as shear zones. So those shear zones also we have to check. The other important aspect of this dam designs is that we have to check the seepage also, because we already explained the purpose of the dam is to store the water, right? So but we should not also allow any seepage, because in embankment dams, if you allow the seepage, the dam will fail. Most of the dams. That's why I'm saying from now onwards, if you see any dam failure in news or anywhere, just try to see how it is failed. You can also check this on the internet. There are so many dam failure cases in India and the world on the worldwide. So just see what is the cause of the dam failure, what is the cause of that project failure. So any that will fit into these aspects, either maybe foundation, seepage, or the spillway. EDA means energy dissipation, whatever the water flowing through the spillway. So there should be some energy dissipation. Otherwise, this downstream area, this completely it will be eroded. So energy dissipation is there, and glove. I think most of the people know glove glacial lake outburst flood. So glove, because of this Himalayan regions, there are so many lakes formed. So it's again a separate topic. I also request all of you please to explore this glove also. So CWC has issued so many guidelines. Recently, 3 guidelines we have issued. One is regarding how to estimate the glove. So just try to explore this Tistra 3 dam failures case study. Tistra 3 dam failed in 2023. So there, that was failed because of this glove, glacial lake outburst flood. Okay, because that sudden glaciers, right? Glaciers, this in the Himalayas regions, they suddenly break out because of so many reasons. Because of earthquakes, because of the heavy rainfalls, because of even so many reasons. Because we have already included all those in the guidelines. Because that sudden volume of glacier lake, it's a lake formed in the Himalayan, in the high altitudes. Those lakes will generally be what happens, no? In the hills, that will be formed because due to that overburden material only in the high rocks. Because if you see in the Himalayan rivers, you will be seeing so many big boulders. So these big boulders will form a lake. So we are studying this dam in complete design. We are making dam of suitable strength, everything. But these Himalayan these glacier lakes, these are all just formed naturally using these natural boulders. So obviously there will not be having enough strength. There will be no seepage control, everything. So because of all these aspects, that natural what you call formed these glacial lakes will fail at any time. So when they fail, because of the water stored in behind these glacier lakes, will cause so much of flood, sudden floods. These sudden floods will come into the dam body because our spillway is not designed. Spillway is designed for whatever data you are measuring. Based on the data, we have estimated our spillway flood discharge. Accordingly, we have designed, but we have not designed for this glacier lake spillway, right? Glacier lake flood. So that's how they also cause very huge damage to the dams. All these Tista 3, you can just note down Tista 3. Just you try to see in the internet or anywhere literature available. You will easily identify how this glove will cause a very huge disaster to a complete river portion. So that Tista river completely damaged. Tista 3 is completely washed away, the dam. Then downstream of those Tista 3, we have Tista 5 concrete dam. Concrete dam also so much damages occurred due to glove. So this is how the major failures happen in all these dams, either through the foundations or through the shear zones, through the seepage, or inadequate spillway designs, or energy dissipation arrangement, and glove, and hydromechanical. Hydromechanical is nothing but gates. So we have to design proper gates. Because see, gates, what happens sometimes if you design gate as per your our design, but during the flood season sometimes gates will stuck. We cannot able to operate the gates. So that's how these gates also very plays a very important role in designing all these dam designs. So next is the abutment slopes. Even because see, like I told, in all our dams we are nowadays we are doing the design of 200-meter dams. So 200-meter dam design first, to start the construction, first you have to do the excavation, right? 200-meter excavation. 200-meter excavation of the river, that side slope of the river. So 200-meter slope should be stable, right? So those abutment slopes also we have to do the stability analysis. Then if you see the issues related to power components, like I already told, sediment is the biggest issue. So whatever data you are measuring, that is very useful, sediment. Then again same slopes, because wherever power hoses are there, we have to again do the slopes excavation. So there will be slope issues. Then there are so many underground, because all these are tunnels, right? Tunnels, even there are underground power houses also. Surface power houses. Surface power house means just like a building, whatever buildings we construct on the natural profiles. But wherever the underground power houses are there, there are big underground excavation we have to do. So those issues, surges, like I explained, what the purpose of the surge shaft is to absorb these surges. Like suddenly, if you close the turbines, that water hammer will generate. To absorb those water hammers, water shocks, you need to have these surges and all these structures, because any structure it's so common. Even if a normal building also, you will see cracks. So in the dams also we'll see cracks, in the pondage and the power houses also we'll see cracks, and flooding, because these power houses generally located close to the rivers, right? So here in the river, when the river is flooded, obviously the power house also will get flooded. So the flooding, where to keep your flood power house levels, how do you protect these power houses during this flooding? Because of this Tista 3 Globe, dam is completely washed away. Even the power house, all the components are got damaged. Then other thing is river diversion. Like I told, to have this construction of this dam, we should have this. We should divert this water so that this dam area should be waterproof. So for that we will be having this copper dams, and also we will be having these diversion tunnels. So again the issues will be there for the copper dams, diversion tunnels, and once we complete the dam construction, we will have to plug. So this, you can see the small color rectangles, these are all plugs. So we will just we will not plug the complete tunnel. We will not complete backfill with the concreting or this thing. Just at the dam axis, at this line, we'll just have this plug. So that plugging. So I'll just these are the major issues of the dams. So at least see, there is no need to worry or anything. Just at least remember these words: how the sediment will the turbines, how the glove, what is glove, how to estimate the glove, and what are the damages of this glove, what is spillway, how do you estimate the design flood. Just you try to uh, years to come into the designs, because from in designs we have 82 level, at least minimum level. So you have at least enough time. So in this time you try to focus on whatever topic, like I have mentioned some more than 10 topics here: hydromechanical, abutment, slope, sediment, trash, slopes, underground. So just any one topic of your choice, just try to focus and try to learn on yourself. If any doubts, we are always there. You can contact us. So now we'll go into different. You need any break? Hello? You need any break?
Adepu, we can take a break.
Yeah,
About
just
10 minutes break.
yeah, 10 minutes break. Then we will continue.
Okay, sure.
Okay.
So we will start again at 11:20. It's 11:10 right now. Okay.
नेक्स्ट करो, पढ़ो मत, यहाँ से बैक कर लो। हाँ, जो आंसर दिखे वो जल्दी कर लो।
Like yeah, so in the first session we know what are the different design units, design directorates in CWC. So at least hope everybody is now clear with the design unit of CWC. We have 5 different directorates and also 5 chief engineer level offices that we call it as either unit, design unit, or design organization. In design, under each design unit or design organization, we have 5 different directorates. concrete dam design, embankment dam design, gates design, hydel civil design, and barrage and canal designs. So these are the 5 different directorates. Each directorate will be dealing with the separate their respective issues. So now we have seen, then we have also seen the different layouts of the projects, like because water resources is for irrigation and hydropower and drinking, right? So we have also seen the layouts of irrigation project and also hydro project. Then we have also seen the different issues likely to come for all these water resources projects with respect to CWC only. So in CWC, with this, the issues likely to come are likely to pay already explained with respect to dam, with respect to power house, with respect to tunnels, and with respect to river. So in every dam design, like we have already seen, how do we select the site, right? Because to select the dam site, first we have to do 3-4 different axes, and accordingly we have to see based on the cost analysis, foundation, geological aspects, water availability, all those aspects. We will finally fix one dam axis. So at the one dam site, how do we proceed for further design of the dam? So obviously the first step is the water availability. So water availability we do by water yield in a particular year and its dependability. Okay. So water yield, I think you are the most experienced than me, at least in this step. So you are all doing all this water availability studies and water collection, all those things. So now, so you see the importance of this CWC design wing. So the first step comes from the field units. You are at the site level. So whatever data you are collecting, that is the first step. First, we have to collect the water availability in series. Then we have to see the dependability. Dependability means the dependability also by now. I think some people, some of you might have know this. So we have to see the dependability because there are different projects. Like if you are planning for a drinking project, you should design the project for 100% dependability. 100% dependability means the drinking, you should provide the supply to the household on every day, right? So 100% dependability means all the time you should able to serve the drinking water to that particular whatever city you are planning. Suppose if you are planning a city's water demand, then at least throughout the year it should able to supply. That's why we are designing a drinking water project for 100% dependability. So accordingly, 100% dependability flows. 100% dependable flows 100% time. That means throughout the year, what is the volume of water available in that particular river? Okay, so that is the 100% dependable value. So obviously, throughout the year values means will be less in very non-monsoon season, like in December, in January. That will be the leanest flow, right? So we have to design that particular drinking water project for the lean flows. If it is a storage project, like if you are storing the water of the monsoon season and utilizing the storage water throughout the year, that is a different issue. But if you are just designing the water as per the water availability, then you should design for the very lean flow seasons. That's 100% dependability. Then if you are designing for the hydro project, that is 90% dependability. That means even the 90% of flows are also enough for the design of hydro projects. If you are designing the irrigation projects, that is 75% dependability. That means out of 4 years or out of 4 months, even if you can supply, even if you can able to provide the water per this voice is coming or not? Hello?
Yes, sir, coming, sir.
Sir, voice is coming, sir.
Yeah. Then yeah. So like I told, right? Drinking project we will design for 100% dependability. Irrigation project we will design for 75%. That means we can take some risk. Like out of 4-5 years, 75% times we can, even if we can able to provide the irrigation water to the fields, that is okay. That's how we have to design the project. Okay. So everybody, I think clear by now the first step. Then we'll go for the second step. So that second step, first we have completed our water availability. Then we'll go for the topographical information. What is topographical information means? We have to do the surveys. I think most of you people will be doing that double level surveying and all the river surveys, right? So the same thing. You have to do the surveys using the total station and LIDAR and all other latest techniques. Even if you have the GIS also, if you can able to generate contours, that is good enough. So what we'll be developing from this step 2, we will develop this contour maps, river cross sections, and area elevation capacity curve. So area elevation capacity curve is very useful in deciding the level of this dam. So that means in one graph, we will try to see with the different elevations, what is the volume of the reservoir and what is the area of the reservoir. So area of the reservoir will be used for to know the submergence of the project, and volume will be knowing what is the volume of that reservoir. So this is the step 2, and we'll go for the step 3. So now we have collected this both data, like water availability we have collected, and we have collected this topographical information, and we have also developed this area elevation capacity curve. Now this next step is to fix the dam height, right? So you can before this step you could have thought of this, even 100-meter dam is also possible, even 50-meter is also possible. But how do we fix that exact height? So that exact height that levels will be fixed in this step 3. These steps you can do as per your convenience, your change also. This is just indicative, not exactly you have to follow as a sequence. So in the fixation of dam levels, so FRL and MDDL. So we all know FRL means full reservoir level. That is the maximum water level we generally we hold in our reservoir. That is full reservoir level. Then MDDL, this is a maximum drawdown level. That means below this level we will not take any water. So that is the minimum level we always maintain in the reservoir. So that is minimum drawdown level, and FRL is full reservoir level. So these levels we will fix using this area elevation capacity curve. How we will fix is, see, if you are designing for the hydro project, you have to do this power potential studies. And if you are doing the irrigation project, you have to do the irrigation simulation studies. So like I told, we have to involve with CEA, Central Electricity Authority. So Central Electricity Authority generally does this power potential studies. They will tell us, okay, you fix this FRL and fix this MDDL like that, okay. Then for the irrigation, we have separate directorate in CWC, Irrigation Planning Directorate. So though they do this irrigation planning, irrigation simulation studies, and they will fix these FRLs and MDDLs. As a designers, we also do on our own. We will also sometimes cross check. And these both are very simple. The concept is nothing but, suppose like it's a simple concept. Suppose let's assume storage at some particular level. There is some inflow. So obviously there is increase in the water in the reservoir. But at the same time, we are taking the water for the power generation, or we are taking the water for the irrigation purpose, right? Again, there will be decrease in the water in the reservoir. So inflow minus outflow and storage. What is the change in storage? So we will have to do this simulation study for the whole year. Sometimes over the 40 years, 20 years, as per the project requirement. Power potential studies is same. Irrigation simulation is also same. There we will know whether whatever storage we are considering, is it serving the purpose as per our needs? Like I told, drinking purpose, we have to design the project for 100% dependability. Hydro project 90% dependability. Irrigation project 75%. So whether we are meeting the requirement or not, that's how we will fix the storage levels, all this FRL and MDDL, etc. Okay, then MDDL, how do we fix? Because that is the minimum drawdown level that we can keep at any place, right? So that MDDL, for that, whatever sediment data you are collecting, right, that is very crucial. So based on the sediment data, we will finalize what will be the sediment volume to be accumulated in the reservoir over some 50 years. Generally, we design the project, any dam project, for 50 years, 70 years, 100 years, like that, right? So in 50 years, because now we are obstructing the river. So when we are obstructing the river, obviously the sediment will deposit there. Whatever you are collecting the sediment data, particular per year per hectare, right? So that sediment will be trapped in that reservoir. So after 20 years, some sediment, that sediment will be accumulated in a huge quantity. So that level we will estimate. That sediment accumulation over the 50 years or some 70 years, 100 years, we will estimate. That is called new zero elevation. So new zero elevation is that sediment will be accumulated in over 50 years or 70 years. So because this sediment, when it is accumulated, we cannot keep our tunnel, right? Because once you place a tunnel there and it will be covered or it will be deposited by the sediment, so we cannot use. So that is why we always keep our tunnels or any outlets or irrigation canals, everything above the sedimented level. After 50 years, what is the sediment level we have to work out, and we have to place our canals over this above the sedimented level. That is new zero elevation level. That is how we have to fix MDDL, and FRL we will fix based on this power potential studies and irrigation simulation studies. Everybody is clear, I think. So next step is, now we know the dam height, because FRL, once you finalize the dam, FRL means obviously dam height will be just 3 or 4 meters above the FRL. That's it. That is the maximum height of the dam. So we know the dam height, we know the contours, we know all this water availability, everything. Like I have already explained in the previous slides. Now the important is to go for the geological data. So this geological information, we will generally do the boreholes, we do the logs, whatever the log means nothing but the collection of data. Because if you do the drill borehole up to 30 meter depth in a foundation, so at each meter, at each depth, what is the different type of rock available, different properties. So that is a log, that is a borehole log. Then I already told we have to do the material properties also. For that we have to do the laboratory testing. So under our ministry only we have CSMRS, Central Soil Material Research Station. They will be doing this material properties, and all this geotechnical information we will collect from GSI, Geological Survey of India. So like you can see the what you call different agencies involvement, right? In the power potential studies we will get it from CEA, and geotechnical information we will get it from GSI, and material properties from CSMRS. So this is the general geotechnical, how do we do the geological information. So geological mapping, that means just we don't do anything here. We just go to the site, we observe what is there as present at the site. Just we'll try to observe what is the rock, what is the, whether it's a soil or overburden or anything. That is called geological mapping. Then we will do some drilling, the borehole. So this is the boreholes. Then sometimes in some high dams, we will have to do this drifting. Drifting means nothing but the tunnel, like manual excavation. It's just a manual height, our height accordingly. So 2.5 meter height, like that only. So we will have to do some tunnels also, small tunnels, to know the what is the geology or rock inside this hills. Then nowadays, geophysical methods. Geophysical methods means it's a electrical resistivity test and seismic refraction. There are so many things. It's nothing but just using this electrical resistivity. So just I will not explain much, because you can explore this geophysical. It's again a, just like remote sensing. Geophysical is also very it's in demand, because without doing anything, without doing any borehole, anything, we can get the data. So we'll see how do we what we get from these 4 different test procedures: geological mapping, drilling, and drift, and geophysical method. So these are the different results from those 4 steps. So in the geological mapping, you can see, like I told, we do not do anything that much thing extra. Only we go to the site. On the contour map, I told we have to prepare this contour map. So in this contour map, you can see this triangular shapes, right? In the small triangular shapes. So this is the indication of overburden. So this green color different shape, this is a different indication of rock. So like that, you can see this different color. That means different soil or different rock. So that's how different color coding will give. This is just a geological mapping. And boreholes, like you can see, the next we have done the drilling, right? So in the drilling, you can see we will collect this cores like this. So you can see the box number also, hole number, and the how much, at what depth, up to what depth we have done this. You can see here 36 to 40.5. So you can see the course, what are the rock. From this, you can easily estimate and you can easily prepare the log. You can see that this arrow indications, that means the depth. This that's how this drilling has progressed. So that's how this depth has increased. So you can see the depth along the depth, what is the rock condition there. And the drift, you can see the small tunnels we have done, right? So those small tunnels will be used to do some testing, in situ testing, and also do the estimate this surrounding rock, how the rock is there. And the last is I told, right, geophysical method. In the geophysical method, you can see we can when you do that electrical current passing and voltage and all those. It's I am just leaving for you for your assignment type. So in electrical resistivity, you will just prepare a maps like this based on the electrical resistivity. So you can easily able to identify different rocks. These different colors means different resistance values. So why different resistance means very good rock will be having high resistivity, very weak rock will be having low resistivity, and if there is any water is a very good conductor of electricity, right? So it will be having very low resistivity. That's how we can have this water level. We can identify different rocks. So this is regarding geological. So you can just see the image. So when we see that this is the dam site, Tehri dam site before investigation. So because if you see here, we don't know anything, just we are seeing the vegetation on the slopes and also some overburden. But what is exactly beneath the soil, that is our important. That is important for us. So that's how. So you can see when we done this, these black ones are the boreholes. So when you do the boreholes, based on this course, you can see different colors. This first one is the overburden, and there's a cyan color is the different color indication. You can see the legend also is there. So different colors will be having different meanings. Okay, so that's how this geological data we try to get from either GSI or you should also know all these differences, because as a designer, as a CWC, we are the major role. We have the major role in design of all these water projects. So we should know all these things. At least basic geology you should know. What are the different types of rocks? How they have formed, and how these geological investigations to be carried out, and how do we plot these sections, geological sections. This is the geological log. That's what I'm saying. You can see this depth wise 0, 3 meters, 6 meters, 9 meters. So as we go to the depth, what are the different rocks? Like you can see in the starting overburden material and weathered sandstone, and then you can see the fresh sandstone. These are useful for to know the limit of the excavation, where we have to place our dam, etc. And there are some laboratory tests, like I told. So these are the different laboratory tests we have to do. Laboratory tests on soil samples, laboratory tests on rock samples, and in situ tests. Just going little speed. This PPT please collect it from NW and just go through all these slides again. Then the important step is the design plot. This is completely in CWC. That is what our HSO unit will provide us. So we have collected this geotechnical information. We have collected this topographical information, everything. The important step is to now the estimation of design flood. So because depends on the dam type, we have to take the different return floods. Because if it is a small dam, so we have to estimate the very low return period, 100-year flood. Return period means everybody knows return period, right? Return period means after how many years it will repeat. If I am saying 100-year return period means in 100 years at least one time it will occur. If I say 1,000-year return period means at least in 1,000 years it will occur once. So as the return period increases, the value also will increase. Suppose 100-year flood, if you say 1,000 cumex, and if I say some 500-year return flood means obviously it will be more than 1,000 cumex. Let's say it may come to 2,000 or 1,500, like that also. So depending on the dam type and dam height, dam heights is divided into 3: small dam, medium dam, and large dams. So for the large dam, we generally go for PMF, probable maximum flood. That is generally approximately equal to 10,000 year return flood. You can see, because large dam means large damage. If the dam gets failed, there will be so much damage. So to avoid those damages, we have to increase the safety in our dam design. To increase the safety in dam design, we have to increase the safety in our flood estimation. So we have to use the more return period floods. So that is 10,000 floods like that. Then we will have to use estimate the diversion floods also. Diversion flood is per flood per copper dams. Like I told, any dam will take at least 5-6 years construction. So that 5-6 years also we should be knowing the probable flood, right, during the construction. So that flood also we will have to estimate. So that is the design flood per copper dams. So this we will be getting in our in-house CWC hydrological unit is there. That is they will provide us this input. So once we got all this information, then we have to select the type of the spillway. We have to select because we know the flood. Now we have to pass that flood to the dam. So there are different types of spillways. We have Vogi spillway, short spillway, side channel spillway. Vogi spillway is just try to explore what are the different types of spillways. Generally nowadays, Vogi spillway means just it's a dam top. Normal conventional spillway at the dam top. But like I told, nowadays sedimentation is the big issue, and also flood is also increasing. So to have this, to face these issues, we are now reducing or taking this spillways to the lower levels. That is called sluice spillways. So sluice spillway is also one type of spillway. Then at this step, because we know the geotechnical information, we know the flood, we know the levels, everything. Here at this step, we also have to finalize this concrete dam or earthen dam, because I explained. But just you can see the difference also here. How do we select between concrete dam and earthen dam? So like I told already, length of the dam, if it is a length is more, you can generally prefer for earthen and rockfill dam because of the cost aspects. But the design flood is more. Concrete spillway, concrete dam is more suitable, because earthen dam, what happens in between the earthen dam, because earthen is just a soil material, right? And a spillway is always a concrete thing. So you cannot just introduce a concrete thing, spillway in between the earthen dam portion. So that is how earthen dam, if you are constructing, it should be a straight portion or complete without any concrete portion. So for that earthen dam, we have to have different options. Like you might be having side channel spillways, short spillways, everything. So that's what I'm saying. Whenever you see next time in any images of any concrete dam and earthen dam, you should observe these vertical aspects, whether the length is more, whether the design flood is more, then the diversion flood also, because earthen dams are generally prone for more failure. As the water flows above the earthen dam, right, it will fail. Whereas the concrete dam, still it will sustain. Concrete dam is a little bit stable in overflowing. Even the water flows above the dam top, also concrete dam still stable. But we generally avoid overflowing of the dams. But earthen dam is completely fail. So that is why while doing the construction, the diversion flood you can see. For the concrete dam, we will consider very less diversion flood, whereas the earthen dams will take more diversion flood, so that during the construction we don't have any accidents or incidents. Then the seismic force, concrete dam generally we do not prefer in the high earthquake region, because it will fail. It's not good enough to absorb the earthquake forces. Generally, in that, if it is that is the only criteria, then earthen and rockfill dams are good for the seismic forces. Then the foundation. See, concrete dam, we always have to place on the fresh rock. Whereas in earthen and rockfill dams, we can place it on the weak rock also, overburden also, if it is a good strength. But always please remember this point, concrete dam, we always place it on fresh rock or a very good rock. Okay, this is the major distinguish between these two dams. So I hope whenever you see any dam images, because you'll be going to different sites at the rivers. So you will meet some people are also measuring the daily water levels at the different dams also. So just try to see these aspects, whether the dam is earthen dam or concrete dam. So if it is a concrete dam, just try to see whether the length is very small or the flood is small, or we have not got this geological we have not got the good rock in the very less depth. Just try to discuss with the project authorities these aspects. So you will be very appreciate these aspects. So that's how we have to fix the spillway. We have to finalize the dam type. Then we have to do the dam top, because we know the FRL only in the step 3. In the step 3, we know the only FRL, that is full reservoir level. But over and above, what happens whenever you go to the dam site, you see so much of heavy winds blow over right over the reservoir, right? So during those high winds, there will be some waves, like in seas, oceans also. That waves will be generated, water waves. So that water waves, that height we have to calculate because of the winds. So that we will call it as freeboard calculations. So because of the freeboard calculations, we have to that freeboard we have to always provide in the dams. So that is we will add it to the FRL. FRL plus freeboard will give the dam top. That is a simple concept. Then maximum water level is what happens. See, most of the dams how they fail. Most of the dam fails in mostly excessive floods. Why they fail? Because what happens, the design flood we know, if the design flood estimated is 1000 cumex, but in the dam your spillway capacity is only 500 cumex. That means 1000 cumex river flow is coming. You can able to pass only 500 cumex through the dam. Then what about the remaining 500 cumex? So that will absorb in the reservoir. If the spillway capacity is less than the incoming flood, that extra flood will be absorbed in the reservoir. So there will be some rise in the water level. So that rise in the water level, we call it as a maximum water level. So first will be FRL, first bottom level with the MDDL, minimum drawdown level. Minimum drawdown level. Then above that FRL full reservoir level. Then above that maximum water level. Then above maximum water level, there will be a dam top. We will add freeboard to the FRL and also MWL. So hope now up to this point everybody is clear, I guess. So that's how we will have to fix the dam top. Then we will, once we know the dam the top and everything, then we'll have to do the stability calculations. So stability also it's different for concrete and earthen dams. For the concrete dams, we'll do the sliding, overturning, and stresses. And whereas we do the stability analysis, slope stability analysis for earthen dams. Then, like I told, once the water is flowing through the spillway, we have to do the energy dissipation also, because the water flowing through the spillway will be having very high energy. So to absorb that high energy, or to absorb that high energy, we should have some kind of arrangements. So I think every BTech all the BTech studies we have done this stilling basin thing. Stilling basin is nothing but based on the hydraulic jump. So hydraulic jump, you all know, there is a Y1 and Y2, conjugate depths, all those things. So that same concept we will use here in the stilling basin. Whereas in bucket type, the water is flows like a jet. It will flow like a jet ski. The water will leave from the spillway and will fall far away from the spillway. So that's what when you go to the any dam next time, just see what is the energy dissipation arrangement there. Is it a stilling basin or bucket type? Then after all these designs, we just do other designs of other, like I told, we have to do the gates design also. We have to do the foundation treatment, because the main purpose of the dam is to store the water. So we should not allow any vertical seepage. So we have to do the foundation seepage resistant. To do the foundation seepage resistant, we do some grouting. So that's how foundation treatment. Even sometimes the dam height is more than 200 meters, 100 meters. The rock is very weak, so we have to improve the strength of the rock, like that. So these are the 10 the steps. You can add more steps. You can include some more steps in between also, but this is the general sequence we generally follow. Now we see the different softwares. So somebody has asked the question in the chat box, right? So what are the different softwares to be used? So these are the different softwares we will use in our dam designs and in our design wing of the CWC. So topographical information, we generally use all our GIS platforms, ArcGIS, QGIS, where we can use our digital elevation models, where we can use digital elevation models. From there, we can use our contour maps. We can generate contour maps like that. And HEC means HEC-RAS. It's a US Army Corps softwares. They have developed some free softwares. I think most of the people you have generated your rating curves for the different sites, right? Rating curve or gauging curve. So that's we can generate it through HECRAS also, because you take generally river cross sections and you try to estimate. I think most of the people I think already worked out this HECRAS and so one more software of HECRAS is HECHMS. So HECHMS also we can use, and AutoCAD is everybody is using, I guess. So then in the design flood, all it's completely GIS related. How to delineate the catchment, how to estimate the design flood, all those things. Then dam top, I already told HECHMS, this maximum water level calculation, you can do it in HECHMS calculations. Then the stability calculations, there the actual civil engineering comes here. The stability calculations we have to use the FEM, finite element analysis also, or normal softwares also there. But nowadays, as we are progressing, we have to use the more sophisticated softwares like FEM analysis. So I recommend some of you please try to explore what is FEM, finite element analysis. So there are so much of material available online. So just go through this FEM analysis. What is FEM? So this Abacus software we'll use, Midas software also we use, and GeoStudio Rock Science softwares we generally use it for earth and dam purposes, because the GeoStudio and Rock Science they both are for seepage analysis, slope stability analysis. So they this we will use it for earth and dam purposes. So all these softwares, whatever I have mentioned here, we use it in CWC. So in STAD, I think most of the you people have already used in STAD in your college days. So these are the dam design steps, and these are the different softwares we use. If any doubt also, please try to comment in chat box, or at the end of the session, we'll have 10 minutes per question and answers. Then I will go in little bit design, little bit detail, like whatever stability analysis, like I mentioned in the step 8, right? For the concrete dam, we will do the sliding water turning and stresses. So do the stability analysis for the concrete dam, because see, all the design is based on the different conditions. If you are designing any power hose or tunnel, dam, anything, you have to first see its reality. In reality, what are the different conditions will occur? Like what is a construction condition, one is extreme conditions, one is the normal conditions. So these are the general philosophy for any design of any component. Even if you design for a gate design also, canal design also, slope design, power hose design, dam design. So you have to design for the construction condition and also normal condition. Normal means regular condition. And one we have to design for earthquake condition. What if earthquake happens? And other condition is what if excessive flood happens? So these are the general design philosophies. Okay. So in dams, we design for these different cases. Like you can see combination A, construction condition, then normal operating condition. So accordingly, we have to take the different loads. Suppose if you are designing any component like gate or any component for the earthquake condition, then you have to take appropriate loads into the designs. So that is the design philosophy. Then in dams, we do this uplift calculations also, because like I told, from the bottom, once you store this water, hydrostatic load will apply horizontally. So there will be some water through the foundation, right? So the foundation, the water will be having some pressure. So that is called uplift pressure. So to reduce the uplift pressure, we provide generally galleries. So these are all just I'm leaving for your work. So just go through the slides also, you will just understand all these things. Just then we'll do the sliding analysis, sliding factor of safety. There is most of the design philosophy is based on the factor of safety. How much factor of safety you are incorporating in your components. Even if your gates, and to lift the gate, you will be having different hoists, different cranes. So the cranes also will be having some factor of safety. Suppose if you are that if the crane is lifting 100-ton gate, so at least we will try to have the capacity of 150-ton crane. That means 1.5 times more capacity of crane we are keeping at the dam places. Same thing in the dam. If the dam is sliding, that factor of safety should come more than 1.5 like that. So these are, you can see the tensions, permissible values of tensions or compressions. You can see what are the different load combinations and what are the different values, stresses Everything is a factor of safety included. So it's a general design philosophy. So now you can see some see problems. I'm just try to mention here. You can see the left side image. See the dam is completed. This is the dam. But what happened just before the initial building? You can see the complete slope stability failure. You can see on the left side image. So the complete slope stability failure. So this failure you can see once they have gone to the side. You can see on the left side. You can see these big cavities formed. So these are the different issues, and because slope stability also you have to consider, and also the diversion tunnels. This is the problem occurred in the diversion tunnels. Like I already mentioned in the first slide, what are the different issues to come in the different component dam? What are the different components? What will be the component issues in the porous, gates, and diversion tunnels? So this is how we see, like you can see the different colors here in the foundation. These are the geological information. So you can see this traps is a good rock, but whereas this blue color, this is all weak rocks. So but we have to have the dam here only. So then we have to do some, but we cannot place dam on weak rock, like just like I have explained. So in that cases you have to do some analysis, finite element analysis. Then you can see the next image, right side image. See, to be treated up to 70 meter below the foundation level. So this all we will remove and we will fill with concrete. So this all we will be finalizing by our FEM analysis, all those things. So this is the in reality. So this is based on analysis. In the reality, you can see the red color, this image, you can see. This is the shear zone. That is a weak rock, I'm saying. Weak rock means just like a clay. If you see in the image, so the junction between these two different color rocks, this white color is a shear zone. That means it's a clay type material. So it will not take any load, right? So it will cause very huge problems in the later run. So to avoid those problems in the initial stages only, we excavate or we remove this, or we have to strengthen this. So they are removing this using this vertical cylinders, right? These are the shafts. So vertical shafts they are excavating, and they will be removing this material, and they will fill it with the concrete. So you can see on the left side image. So these are the shafts they are doing this. So you can see one more image here, slope stability. You can see all these vertical lines. These vertical lines. So these are all vertical lines are piles. This is complete soil material. This complete, you see, this is the slope. So in the slope, you see complete. This is the soil material. To strengthen this soil, you can see vertical. Vertical, is it possible to stabilize this soil material? It's generally not possible, right? So that's what I'm saying. Every project is a unique project in water resources. So you have to design accordingly. So just some more issues I will try to explain. So like in barrages also. So this is the glop issues. Like you can, I will just. So this is the generally embankment, right? So embankment, just to try to focus on the heading. Earthen dam, central core, and positive cutoff. Positive cutoff means you can see in the number 2 here. Wherever the rock is available, we will just have this clay core. One is just you can see the nomenclature. One is positive cutoff. That means we are extending our clay zone so that water is not seeping through here. So this design. This is the only basic 2 designs only. So this is the second design. So this is the first design. The rock is at the very deeper depths, 80 meters, 100 meters. Then your upstream, you can see the difference between this clay core. So we have to extend this upstream blanket, and we should have this vertical this thing. This is called relief well. It will collect the seepage. Because if you don't collect the seepage, it will erode and it will create problems. Anything, the designs, the problem is to avoid the seepage. If you can't avoid the seepage, collect the seepage. So you can see the difference. This is the basic difference design of this embankment dams. So further, suppose if you cannot provide this kind of layout, either you can go vertically some obstruction for the seepage, like this plastic concrete cutoff wall. So this cutoff walls means you can see this is the earthen dam portion. In the central, we will be excavating some 1.2 meters like that. We'll completely remove that material and fill with the concrete, cement concrete. So you can see the wall. So the complete wall is prepared at this portion, like this diaphragm wall. So that seepage is stopped. So other measures are like you can see we will do some jet routing. This is a high pressure jet routing. So if you do the jet routing, you can do the vertical walls will be formed in the foundation, and also sometimes you can have this soil treatment also. In the bottom image you can see soil treatment. That's how you can stabilize and reduce the seepage using the jet routing, soil treatment, everything. So this is what I am saying about Tista 3. These are the images of Tista 3. You can see the damage caused by glove. So earlier, this is this top image was the dam existing. You can see the dam. After that, you can see same image. You can see that left side portion, that spillway is there with the boulder. You can see big boulder came. Like I told, no, this glove is generally these are the lakes formed by this very big boulders or moraines. So that will be flowing when the glove that breaks. So that you can see the damage caused by gloves. Entire dam washed away. This is 1200 megawatt project. So you can see here, completely 80 meter or 90 meter dam height was washed away. So the downstream of that project is Tista 5. So Tista 5 also you can see so many damages, and also there are some slope damages also happened here. So you can see this. You can see the dam. This is the spillways, right? So you can see all this. You can see that this gate cutting. This is the gate hoisting arrangement. You can see the cutting. This is not cut by manually. It was cut by flood. You can see this much thick steel was cut by glove flood. Now you can see it's what you call devastating effect of these gloves. So one more general aspect is, like I told, we should not allow overtopping. So once you do the overtopping, you can see you cannot, because it will cause other problems, because it will cause the abutment problems. And you should, in the designs, you should also have the instrumentation data. You should have very good instrumentation. Instrumentation means nothing but it will measure the readings at regular intervals. Because while constructing the dam also, you should have some instruments placed in the dam body that will give instruments like stress, what is the stress, what is the strain, what is the uplift, everything. So this is one case study in America. What they have done is when the reservoir is filling, it was giving wrong readings. Earlier it was to give the FRL level, but the instrument got failed. So it was giving wrong readings, so they don't know exact level. They thought, okay, it's working well. They kept on pumping the water into the reservoir. So ultimately, I told earthen dam fails in overtopping, right? So after that, you see what happened. So they kept on pumping the water up to the dam top because of the faulty. See that this is the problem. This is the dam failure happened. So if you just look for I will just take 5 more minutes. Nothing. After that, we'll take any questions. So if you see. Either it can that canal can take from the dam body itself, either right bank main canal or left bank main canal. Sometimes what happens, dam will be very high, like 50 meter, 60 meter height, but your command will be, but in the canal you should give some, but you should maintain head, and also you should maintain very less velocity, right, to avoid erosion. And also commands will be far from the dam body, dam place. So in that case, you will be having, generally you'll be having pickup weir. That means very small structure just downstream of this dam, from where we will be having again canals. You can see that this is the difference between these two layouts. So that's what I'm saying. Whatever I'm brief I have explained here, just try to observe whenever you go to any dam, any irrigation project, why they have selected that particular kind of dam or particular site, and why they have taken that particular layout. Why they have taken left bank canal only? Why they have taken right bank canal? Why they have done this tunnel on this particular bank? like that. So these are the just different components you can see. Earlier in the left side image, this is just a weir. So weir means just having 1 or 2 meters concrete structure, just like a rubber dam I told, right? Whenever we need, we will inflate it. So 1 or 2 meter storage we will have, and we will divert the water. Then the further advantage is the improvement is the barrage. Barrage means just we will have a gate here. So you can see in the next image, second image, right? So that's the difference between barrages and weirs. So you can see this is a simple weir. You can see here there is a gate. There is no. You can see there is no gate. Nothing. Whenever you want to store here in the right side image, you can see just they will place this wooden planks or any steel plates to store the water up to a certain height. When there is no requirement, they will just lift those wooden flaps or the steel gates by manual thing. So this is a general, very typical layout of barrage. It's a very complicated. But when you see, it's all very easy. I will just explain in the cross section. These are the some barrage design steps I have mentioned here. Just go through these slides. You can see the failure here. This is very recent in Tilapara barrage in West Bengal. You can see how the barrage is failed. Because what happens, the importance is obviously, like I always told, in major water resources project, problems is the seepage, erosion, and foundation issues. So in embankment and barrages, seepage is the biggest issue. And also in barrages, erosion. You can see in the downstream side, these concrete blocks, you can see up to here, that bottom water level is almost 5-meter difference. Actually, in the beginning of the project, like 30 or 40 years back when it was constructed, the riverbed was up to this concrete level. But over the time, it got eroded. Obviously, the barrage generally be placed on the sands only, right? So sand got settled, and you can see the cracks. You can see it's complete failure of this barrage. Along the length, you can see all the piers got failed at same point. That means at that point, complete settlement happened. So this is the barrage section. So you can see upstream sheet pile and downstream sheet piles. We generally do provided for the stopping of this erosion. Sometimes we provide intermediate piles. So the other important is that we have to estimate the seepage using the coast loss theory. All this you have worked out in your BTech in our BTech times, right? How do we estimate this seepage length or critical exit gradients? What is the depth of the sheet piles? And what are the different pressures? So that is the only concept of this barrage design. So rest all we have completed about concrete dams, embankment dams, barrages, canals, power houses, and gates, everything, and even slope stabilities also. So if any question is there, we will take up for a few minutes, then we will break up. So any questions? Hello?
Uplift pressure in dams, we use drainage galleries. Sir,
Yes, yes.
where it is provided, and do you have any picture of that?
There are right now in my PPT it is not included, but just Google it also, or you can take. That's what I'm saying. If you want any images or any quotes or any literature, just try to get the number from my number. Just WhatsApp me and I will send you all those images.
Okay.
You can slide in the slide. This is just an indicative, but better galleries are there. I will share you. No problem. That's not an issue.
Okay.
Any other doubts?
सर इस डिजाइन प्रोसेस में जेई और एडी2 का क्या रोल होता है सर, मतलब इसमें क्या काम करते हैं?
No, that's what I'm saying, right? In our design unit, we don't have actually JE post, but we have many AD2 posts are there. Right now in our directorate, in my directorate, there is no AD here. We have AD2, so that we are completely dependent on AD2. So AD2, so many posts are there in all the units. Even if it is hydrology, even it's a dam safety, DSO, all other 3 design organizations. It's AD2 is so many posts are there. That's what I'm saying. utilize this JE period to first identify your choice, your interest, focus your interest of subject. Like I have explained all these subjects, right? Just focus on that subject, try to get some information during your JE career, and when you come back to CW's headquarters in Adepu promotion, just let us know. We will definitely give proper posting. We'll try to request based on your interest.
Okay, sir.
Adetus are completely involved in all the design aspects.
सर वो कैनाल कैसे अलाइन करते हैं सर, वो थोड़ा मतलब ऐसे रफली आप बता दीजिए।
जैसे केनाल का देखिए, मतलब केनाल में क्या है ना, मतलब डैम से हम डैम, आई विल जस्ट शो दैट इमेज। So if you see here this canal मतलब layout, either मतलब if डैम छोटा हाइट है, सपोज मान लीजिए 30 मीटर से 40 मीटर डैम हाइट है ना, तो 30-40 मीटर से सीधा डैम से ही कैनाल लेके जा सकते हैं। एंड कैनाल में आपको 3-4 डिफरेंट कैनाल्स है। We have different canals. One is contour canal, one is ridge canal, one is what you call side channel canals. So there are different canals. First, you please try to explore what is contour canal and what is ridge canal. Contour canal means it will follow particular level. So that means the whatever command below that particular level, the canal will supply the water. Whereas the ridge means, you all know the ridge definition, right? All the basins, river basins means the river basin line is the ridge line, right? Godavari, Krishna, suppose if you see Godavari ridge, Krishna, that is the ridge. So if you plan in subcatchments also, if you plan a canal along that ridge, that means it will supply water to the both sides, that side and this side, right? Then that is the different type of canal. Then that full supply level of the canal we will plan generally based on the command area, the highest point in the command area. Suppose 1000 hectares area is there, you have to supply the water to the 1000 hectares. So that maximum, that highest level of that command area you will find out. So that is the point. That is the point from where your canal starts. So then from that you have to do the back calculations. So that is the minimum point, right? Canal. So from there you have to do the head calculations up to the dam. Likewise, you have to fix the dam FSL, full supply level of the canals. So that is a simple. That's how I explained in 1 minute. But you can just you can ask me later on also. I will just provide the material. So that is a concept. First, you estimate the maximum point of the command area. So that is the top, farthest point of the canal. So from there, you have to start towards the dam side to back calculation of the head calculations. Accordingly, you as per the gradient, you have to provide the full supply level of the canal based on the demands also. Okay.
सर ये आप जैसे ये एम्बैंकमेंट डैम सर वर्ड यूज कर रहे थे सर।
हाँ।
तो सर मतलब एम्बैंकमेंट एंड डैम, मतलब एम्बैंकमेंट इज जस्ट अ स्मॉल डैम ना सर?
नहीं, दैट्स व्हाट आई एम सेइंग ना। अगर तेहरी डैम देखिए 260 मीटर डैम है, मतलब 260 है। देखिए वो भी रॉकफिल डैम है, मतलब रॉक, मतलब एर्थन डैम का कैटेगरी सेम ही है। रॉकफिल डैम में भी सेंट्रल में क्ले कोर रहता है, एर्थन डैम में भी सेंट्रल में क्ले कोर रहता ही है। तो एर्थन डैम्स यस, मतलब वो 30, 40, 50 मीटर तक जा सकता है, उससे ज्यादा जाना है ना। एर्थन डैम्स में आपको ज्यादा मटेरियल यूज होता है। रॉकफिल में भी जनरली, बिकॉज रॉकफिल में वी कैन स्लोप को थोड़ा स्टीप कर सकते हैं। सो रॉकफिल में थोड़ा क्वांटिटी कम हो जाएगा, एर्थन डैम्स में थोड़ा मटेरियल ज्यादा यूज हो जाएगा। दैट्स द ओनली डिफरेंस। सो इफ यू हैव enough quantity of material available, you can go for earthen dam also, but preferable is the rock fill, because obviously cost again will play a matter, right? So that's the difference.
सर मतलब सर embankment dams you have said sir na many times, so I'm little bit confused sir. Embankment is a small dam na sir?
No, that's what I'm saying. Even 30 meter, 40 meters also embankment dams are all there. Earthen dam, embankment dam, rockfill dam, they all come into the same category.
Okay sir.
Adepu, I think his question is ki what is the embankment dam?
What is the embankment dam? Then एक बार आपको मैं दिखाता हूँ। So if you see this slide, okay,
Yes, sir.
is it visible?
Yes, sir.
So you can see this. You can see types of earthfill and rockfill dams, right? So there, if you see complete that first one is homogeneous earthen dam. So if you have completely have same material, because there is no any other material, completely homogeneous material, that we what you are referring is that embankment dam, small dams. But there is a height considered, like I told, right? Because you can see the slopes also. If you see, all the images are of same width, right? But you can see the first image, the width of the first image is more compared to the other dams. So as you increase the height, the seepage also will increase. So to stop the seepage, you should have this clay core and also this upstream slope and downstream slope, because as the height of the dam is increasing, you should also have more resistant material, right? So soil is generally not that much resistant. So that's why we are increasing, giving this outer layers as you can see boulders. That is why the rock fill is coming. You can see the variation. First one is homogeneous. Then we are going with the centrally clay core material. Even if you want further optimize,
Sir, ye all three, all four kind of dam, we can call it earthen embankment dam. Hello, sir.
I think we are again Raghavendra is missing. So just to clarify here, actually एम्बैंकमेंट डैम का मतलब होता है कि एक ऐसा डैम जिसका बेस जो देखेंगे ना वो बहुत वाइड होता है। जो अगर आपका जो प्रेशर फोर्सेस जो आते हैं ना डैम के ऊपर उनको प्रिवेंट करता है थ्रू फ्रिक्शन। और एम्बैंकमेंट वो यूजुअली रॉकफिल अर्दन डैम ये सब डैम होते हैं। और अगर डिक्शनरी मीनिंग से जाएंगे तो मतलब ऐसा होता है कि आप एक ऐसा स्ट्रक्चर खड़ा करने वाले हैं विच विल जस्ट एक्ट लाइक अ माउंटेन। एक माउंटेन बैरियर की तरह वो खड़ा होगा और पानी को रोकेगा। ठीक है। उसका दूसरा ऑल्टरनेटिव होता है ग्रेविटी डैम, जो हमारा कंक्रीट ग्रेविटी डैम होते हैं, जो अपने वेट के कारण जो है पानी की स्ट्रेसेस पानी के फोर्सेस को है वो बियर करता है। So earthen dam, rockfill dam, these are under the category of embankment dams. ठीक है?
yes,
So
yes,
means
that's what
मतलब
that's
sir
what
embankment dam, सर कंक्रीट डैम मतलब जो ग्रेविटी के थ्रू रेजिस्ट करता है सर सारा प्रेशर, और उसके बाद सर एक जो आर्च डैम हो गया, ये ब्रॉड कैटेगरी हो गई ना सर?
नहीं,
Adepu, you there? Hmm. So meanwhile, अच्छा आर्च डैम का आपने पूछा तो आर्च डैम इज it's only because of its shape it's called an arch dam. It can be a gravity dam. Arch dam are usually gravity dams. तो उसका शेप जो होता है वो आर्च के शेप में होता है, इसलिए उसे आर्च डैम बोला जाता है। उसमें जो उसके स्ट्रेसेस होते हैं वो आपके जो रिजर्वोयर के साइड में जो क्या बोलेंगे जो माउंटेन्स होंगे उनकी स्ट्रेंथ अच्छी होनी चाहिए ताकि वो अपने जो स्ट्रेसेस हैं वो साइड वाले माउंटेन रिजेस के ऊपर अपना स्ट्रेस ट्रांसफर कर सके।
यस, ये एक्चुअली स्टार्टिंग में जो वॉइस का डिस्टरबेंस था ना, शायद उसमें मिस हो गया होगा। आई हैव एक्सप्लेन्ड दिस इन स्टार्टिंग व्हाट यू कॉल in the initial lectures. So anyway, that gravity is the basic difference, gravity and because all the embankment dams, they get the strength by shear strength, because we all know that shear strength, more Coulomb formulas, all those things. In the gravity, it's completely by weight. The weight is giving the stability, whereas in embankment dams, soil strength, soil shear strength, because of the shear strength of the soil based on the, we all know the C and pi, right? C and pi of the soil. Based on the shear strength, that dams are being designed, embankment dam. In that embankment, we have all these different four types of dam: arch dams, roller compacted concrete dams, and masonry dams and concrete dams. These are all comes under gravity dams. This is the basic difference.
Okay, sir, got it.
Okay, any other query from any of the participant?
यस सर, गेट डिजाइन से संबंध में आवाज ही नहीं आ रही है सर की।
पूछिए मीनवाइल
आवाज
हाँ
आ रही
पूछिए
है?
हाँ पूछिए।
सर गेट डिजाइन के बारे में थोड़ा सा बता दीजिए सर, जो मैकेनिकल से रिलेटेड है।
एक्चुअली उसके ऊपर कल सेशन है और वो चास्कर साहब चीफ इंजीनियर एनडब्ल्यू है, वो सेशन पूरा गेट्स के ऊपर लेने वाले हैं कल।
ओके सर, कल देख लेंगे, ठीक है सर।
So to give the idea of what are the different components, what are the matlab we CWC we do design in different directorate, that is the purpose. But even like Saurabh told, right, you have other lectures planned for this separate designs, so that will be covered. Even if it is not there, just try to get my number and you can ask anytime.
ओके सर, थैंक यू।
Adepu, we have already provided your number to them, so
Yes, yes.
I hope they will be contacting you if required.
Yes. Okay, I will.
Again this connection issue. So any more query from any of the participant?
Roll up, sir. Water gallery in dam.
ड्रेनेज गैलरी आप पूछना चाह रहे हैं?
Drainage gallery, sir. Drainage.
See, matlab the basic problems in all the dams is, right, to collect the seepage. Seepage is the basic issue in all the dams, concrete dam ho, embankment dam ho, जो भी हो। तो जितना सीपेज हो उतना अपलिफ्ट प्रेशर लगेगा डैम के बेस पे। तो अपलिफ्ट प्रेशर का मतलब है जैसे ग्रेविटी है, हमारा डैम्स आर ग्रेविटी डैम, बाय वेट वी आर डूइंग द स्टेबिलिटी, राइट। सो ग्रेविटी के अपोजिट है अपलिफ्ट है, तो बाय अपलिफ्ट द वेट इज गेटिंग रेड्यूस्ड। तो जैसे वेट रिड्यूस हो गया तो फिर डैम का स्टेबिलिटी भी कम होता जाएगा। तो टू रिड्यूस द अपलिफ्ट, टू रिड्यूस टू completely stop this seepage, we will generally provide these galleries. From the galleries we will have these drainage holes from where we will collect the seepage. So once we collect the seepage, that means we are collecting the seepage, means we are reducing the pressure, we are reducing the uplift pressure, so we are increasing our self weight. So that's how we are increasing the stability. So that is the basic purpose of the galleries. But in the galleries we will be having instruments also. So many instruments are all again installed in the galleries, and some galleries are there for inspection purpose. So there are three basic purposes. One is for the reducing uplift by upstream galleries, then having these instruments, and also for inspection purpose.
Okay, sir. One more doubt. ठीक है. Okay, sir.
Okay.
Thank
So
you,
in Adepu, just in continuation to this earlier query, हम लोग अर्दन डैम में गैलरीज प्रोवाइड करते हैं क्या?
नहीं.
Is it required?
Earthen dams में we generally don't provide. Only in Tehri it was provided, but remaining most of any dams we generally don't provide earthen dam. But in earthen dams, how do we collect the seepage is through the filters. After the clay core, we generally have sand filters. So sand filters collect the seepage. In concrete dams, these galleries collect the seepage. In earthen dams, these sand filters. That's what I've told. If you see any embankment section, you will have the clay core. Just downstream of the clay core, you will have some filters, sand filters. So that sand filters will collect the seepage.
Okay, thank you.
Sir,
And
जो सर
बताइए।
रूरल में पॉन्ड होता है, that is also type of dam ना, rural reservoir, sir, which we built in RRR.
हाँ वो तो स्मॉल डैम्स है, वो तो मतलब 5 मीटर के एम्बैंकमेंट्स है, स्मॉल एम्बैंकमेंट्स।
तो सर उनका जो width of embankment कैसे डिसाइड होता है सर, on which factor?
नहीं, दैट्स व्हाट आई एम सेइंग ना, ये कंप्लीट डिटेल डिजाइन में जाएंगे तो आई विल जस्ट प्रोवाइड सौरभ लिटिल बिट व्हाट कॉल फर्दर कोड्स. Just he will share you the codes. Just go through those one or two codes. You will able to easily know all these differences. Okay, that embankment is only one code is there. Just go through that one code. You will clearly understand all these design aspects. Because it will take much time. I can explain in 2 days also, but but I just have to give overview. मतलब I try to complete मतलब whatever maximum possible I have covered here.
सर
Okay, sir.
इतना हेवी स्ट्रक्चर सर, अर्थक्वेक का क्या क्या इफेक्ट हो सकता है?
earthquake में देखिए बड़े बड़े डैम्स में जैसे कंक्रीट डैम है तो क्रैक्स हो जाता है, तो आपका बिल्डिंग्स में भी देख सकते हो ना, जैसे कोई भी earthquake होने के बाद तुरंत टीम्स जाता है, इंस्पेक्शन टीम जाके बिल्डिंग्स में क्रैक्स देख लेते हैं और कोई इंपॉर्टेंट स्ट्रक्चर्स में क्रैक्स देखते हैं। सेम डैम्स में भी क्रैक्स को हम लोग देख लेते हैं, और डैम्स में कहीं सेटलमेंट हुआ है, एम्बैंकमेंट डैम हो तो सेटलमेंट देख लेंगे, कंक्रीट डैम होगा तो क्रैक्स देख लेंगे।
सर
अभी क्या सर एनडीएसए देख रहा है क्या, अगर किसी डैम में सीपेज या पाइपिंग की वजह से फेलियर होगा या कुछ भी होगा
यस
तो एनडीएसए देखता है या सीडब्ल्यूसी?
यस, देखिए पहले जब एनडीएसए से पहले, जैसे डैम सेफ्टी एक्ट से पहले, ये सब हमारे सीडब्ल्यूसी के अंडर में होता था, लेकिन जैसे ही एक्ट आ गया था तो उसी समय एनडीएसए सेपरेट ऑफिस भी बनाता है एज पर एक्ट। तो नव जो भी डैम कंस्ट्रक्शन से पहले है, अगर जो भी डैम डीपीआर लेवल पे है, जो भी डैम को डिजाइन करना है, वो अभी भी सीडब्ल्यूसी के अंडर में है। तो लेकिन जो कंस्ट्रक्शन हो गया है, जो ऑलरेडी एग्जिस्टिंग है, उसका पूरा अभी एनडीएसए में ही इंस्पेक्शन होगा। तो ऑल द डैम ओनर्स दे आर डूइंग ऑल द इंस्पेक्शंस रेगुलरली, तो एनडीएसए के अंडर में आता है। अगर एनडीएसए से कोई मैटर टेक्निकल और एडवाइस चाहिए तो एनडीएसए ऑलवेज रिफरिंग द ऑल द मैटर्स टू सीडब्ल्यूसी, सो वी आर असिस्टिंग सीडब्ल्यू एनडीएसए इन ऑल द मैटर्स।
सर एक चीज और सर पूछनी थी सर, जैसे हम लोग सर जब पढ़ रहे थे तो सर वियर और एक नॉचेस सर पढ़ते थे सर, नॉच का कभी यूज नहीं है क्या सर प्रैक्टिकली? मतलब
देखिए नॉच का मतलब क्या है, नॉच का मतलब इट्स जस्ट लाइक ए मेजरिंग डिस्चार्ज, राइट, ट्रेपेजॉइडल मतलब रेक्टेंगुलर एंड ट्रायंगुलर। सो ये जो गैलरीज में हम लोग जो सीपेज कलेक्ट कर रहे हैं ना,
जी सर।
तो गैलरीज में जो सीपेज कलेक्ट कर रहे हैं उधर मेजरमेंट के लिए हम छोटा छोटा सा नॉचेस है, ट्रायंगुलर नॉच है, रेक्टेंगुलर नॉच, हम गैलरीज में, तभी मैंने बोला था गैलरीज का पर्पस है सीपेज कलेक्ट करना, इंस्ट्रूमेंटेशन रखना एंड इंस्पेक्शन के लिए। तो जो इंस्ट्रूमेंट का मतलब है, इसमें एक ट्रायंगुलर नॉच, रेक्टेंगुलर नॉच भी रखता है उधर, हम लोग कितना सीपेज कलेक्ट हो रहा है वो उससे पता चल जाएगा हमको।
ओके सर, मतलब ऐसा जो उसको रिजर्वायर के लिए मतलब
नहीं
कभी
नहीं, वो तो
नहीं यूज
स्पिलवे ही हो
करते।
गया ना, जैसे स्पिलवे रेक्टेंगुलर हो गया ना, स्पिलवे का रेक्टेंगुलर है तो यू
जी
कैन
सर।
इट्स लाइक रेक्टेंगुलर नॉच ओनली। तो स्पिलवे का भी एक कैपेसिटी, हम लोग जस्ट यूजिंग द सेम फॉर्मूलाज वी आर एस्टिमेटिंग द स्पिलवे कैपेसिटी, दैट इज आल्सो वेरी बिग नॉच।
ये थोड़ा कंफ्यूजन हो रहा है शायद यहाँ पे। प्रवीण प्रवीण ही है ना? एक्चुअली आपने जो पूछा है वो वियर्स एंड नोचेस, वियर्स इज अ डिफरेंट स्ट्रक्चर totally, and notches are totally different. Notches are very small structures which are used only for measuring the discharge, है ना? और वियर्स को आप कंपेयर कर सकते हैं बैराजेस से। तो वियर्स आर रिलेटिवली बिगर स्ट्रक्चर जो वाटर स्टोरेज के लिए आपका यूज होता है ना?
जी सर।
Usually weirs and barrages are similar. Barrages are just structures with gates and weirs are structures without gates. That's the difference between barrages and weirs. But notches are very small structures जिनको आप छोटी छोटी नालियों में लगा सकते हैं डिस्चार्ज मेजर करने के लिए।
ओके सर।
So I think we can मतलब we can you can ask me anytime, I will always support you. So Saurabh, I think मतलब the
हाँ
questions will be many.
हाँ
So
हाँ
you
हाँ।
just
Just Adepu, there was one question in the chat box. I don't know whether it has been answered or not, but why there is no dam in the plain area of Ganga basin? Is it due to the requirement of long length of the dam, or other things also involved?
so like in there are like our India is also of different geology मतलब topography, right? In Himalayas, if you see in Uttarakhand and Jammu Kashmir and Northeast, those are all very steep terrains, whereas in this Ganga and all these deltaic areas are there very plain. So in Ganga, if you see the Farakka barrage is there already. The Farakka barrage is a very small height, but because of this Farakka barrage small height also, you can see so much of submergence. It goes up to Patna. Even the Patna or any other some submergence issues, Bihar always highlight about this Farakka project. So the Ganga itself is a very plain river. So if you have even some
Okay, so we have again lost you, Raghavendra. But just to continue, अगर हम गंगा बेसिन में अगर कोई डैम बनाते हैं प्लेन एरियाज में, अगर मान लीजिए आपका 5 मीटर का भी आप हाइट का डैम बनाएंगे, तो वो 5 मीटर डैम के लिए भी आपका सबमर्जेंस एरिया जो है वो बहुत ज़्यादा होने वाला है। तो उतना सबमर्जेंस एरिया होगा, उतनी पॉपुलेशन अफेक्ट होगी, उतना लोगों को आपको रिहेबिलिटेट करना पड़ेगा। तो ओवरऑल द इकोनॉमी ऑफ द प्रोजेक्ट विल नॉट बी वायबल। तो ये एक और रीज़न है कि हम लोग प्लेन एरियाज में नहीं बनाते हैं। यूजुअली वी सर्च फॉर वैली काइंड ऑफ वैली फॉर्मेशन जहाँ पे हमारा सबमर्जेंस कम हो। हाँ, अडेपू यू आर बैक, सो यू मे
So
कंटिन्यू।
that is the yes, that's what you have rightly explained. So depending upon our requirement, if there is no requirement, because Ganga we have plenty of water, and you can plan with the very small structures, 1 meter, 2 meter check dams like that also. Even with the Parakka, that back water is coming up to Patna. So any dam you cannot plan up to Patna.
I think there is continuous connection issue. So actually फरक्का बराज प्रोजेक्ट हमारा लास्ट कंट्रोल पॉइंट है गंगा रिवर पे, जिसके बाद गंगा जो है बांग्लादेश में फ्लो कर जाती है। तो अभी उससे वेस्ट बंगाल से अपस्ट्रीम में बिहार लाई करता है, ठीक है। नाउ बिहार इज कंटिन्यूसली कंप्लेनिंग दैट द बैक वाटर्स ऑफ फ्रॉम फरक्का बैराज प्रोजेक्ट विच इज एट द लास्ट पॉइंट ऑफ गंगा व्हेन इट एंटर्स बांग्लादेश, वहां से आपका बैक वाटर जो है फरक्का प्रोजेक्ट का पटना तक जाता है बिहार में, जिसके कारण वहां पे बैक वाटर होने की वजह से पानी स्टिल होता है और वहाँ सेडिमेंटेशन का इशू क्रिएट होता है। तो वहाँ पे सेडिमेंटेशन होगा तो रिवर का कोर्स चेंज होने का भी बहुत चांस रहता है, जिसके कारण रिवर्स में फ्लड्स आने का चांस है। तो वो भी इशू है एक, ठीक है। तो वही है। और मतलब फरक्का तो आपका कोई डैम भी नहीं है, जस्ट एक बैराज ही है, उसके कारण आपका पटना तक जो है वो फ्लडिंग का इशू जा रहा है। तो ये कुछ इश्यूज हैं हमारे प्लेन रीजन्स में अगर हम डैम बनाते हैं तो।
और सर ये बैराज के सर गेट कब कैसे कितने खुलने हैं सर? मतलब ये कोई सर रेगुलेशन होता है या फिर मतलब सर आपने मतलब खुद से ही डिसीजन लेके लोग वहां पे ऑपरेट करते हैं सर?
नहीं, खुद से कैसे करेंगे, वो तो शेड्यूल जैसा रिक्वायरमेंट है पानी की, उसके बेसिस पे उनको रेगुलेट किया जाता है ना। एक्चुअली बैराजेस आपका ना वो मतलब वो रिजर्वोयर की तरह काम नहीं करता है। बैराजेस आर नॉट मेंट फॉर द पर्पस ऑफ स्टोरिंग द वाटर, दे आर क्रिएटेड ओनली फॉर डाइवर्टिंग द वाटर, है ना। थोड़ा सा कुछ नॉमिनल आपका हाइट रेज करके वो बैराजेस का गेट आप क्लोज कर देंगे, नॉमिनल कुछ हाइट रेज होगा पानी का रिवर में, जहाँ से आप उसे कैनाल के थ्रू डाइवर्ट कर सकते हैं। सो दैट्स द पर्पस। फर्दर बेस्ड ऑन द इनफ्लो टू द बैराज एंड व्हाट इज द रिक्वायरमेंट, व्हाट आर द यूटिलाइजेशंस फ्रॉम दैट बैराज, उसका एक शेड्यूल चार्ट आउट करते हैं, कैसे रेगुलेट होगा, अकॉर्डिंगली उसको कंट्रोल करते हैं।
जी सर, मतलब जैसे कि वो देखना पड़ता होगा ना सर कि पीछे मतलब अप स्ट्रीम में कहीं फ्लड ना हो जाए
हाँ,
अगर गेट
डेफिनेटली
बंद
डेफिनेटली
रखेंगे, या फिर
डेफिनेटली।
डाउन स्ट्रीम में ना तुरंत ही आ जाए।
हाँ हाँ हाँ,
जी सर।
वो सब
मतलब तो वो
रहता
सर एक कुछ मतलब बनाते हैं ना सर, मतलब कुछ होता होगा ना सर?
है। हाँ, वो रहता है ना, इनका क्या बोलते हैं उसको।
नहीं मैं बताता हूँ। बेसिकली अरुणाचल में देखिए अभी बहुत बड़े बड़े डैम बन रहे हैं ना, तो बहुत बड़े डैम्स बनने के बाद भी हमारा जो स्पिलवे रिलीज है ना बहुत कंट्रोल्ड है। इट्स ऑल प्रोजेक्ट स्पेसिफिक, इसी के लिए तो एनडीएस ये बना है, इसी के लिए तो डैम सेफ्टी एक्ट आया है।
So I think there's continuous connection issue, and Adepu, we have again lost you. So I think we can close this session now, and as most of the queries have been answered, and it's also time. So thank you, Adepu, if you can hear me. Thank you so much for taking these two sessions on the overview of design of water resources projects. Though there were some issues regarding the connectivity, but still I hope that the participants got an insight on what are the CWC areas of work related to the design of these structures. So thank you so much on behalf of NWA. I extend my gratitude to you, Adepu, for taking these sessions. And thank you now. And I request all the participants that you may please take a break, and we'll be starting with the post-lunch sessions at 3 o'clock today. So please join. Okay.
Yeah.
Thank you so much.
Yeah. Thank you. Thank you.
Adepu, you are back. So
Yeah. Thank you.
you.
But anytime we are ready, we are there. We are CWC people only. So within our organization, we can always help. Okay.
Okay, Adepu. Thank you.